It's on. So again, I haven't done a single one of these problems, so we have to think about it. The thing is that I cannot be able to switch from screen. Yeah, I might be able to. I might have to do that because I didn't take the notes. So you said that you wanted to start by number 4, which is basically this problem over here. So it's a car of mass 2,000 kilograms traveling at a velocity of 20 meters per second. Is stopped by a spring damper mechanism. If the stopper mechanism does not have to deform more than 20 centimeters in t equal 0.5 seconds, determine the stiffness value for K1 and K2 so that K1 equals K2. Okay. So let me just do a figure again at the beginning, and let's see how we can solve this problem. So exam 1. Problem 4, so basically we have damper over here, that's spring over here. One. C. Okay, and here you have your whatever car. Moving with the velocity v and mass m. So we know that m equals 2,000 kilograms, and that v equals 20 meters per second. We don't want this to bend more than, what is it, 20 centimeters in t equal 0.5 seconds. Now we need to find K1 and K2. So let's see. I mean, really, I see multiple ways, to solve this problem, but, everything will depend on your assumptions. So I mean, I don't think there's one way to solve this problem just. There's just one way to solve it. So, okay, let me tell you what I have in mind. In this problem, what I mean, my issue right now is to say, do I treat the acceleration of the car when it's coming, or when the car is going to hit the bumper, so the deceleration of the car, as constant, or do I treat it as a function of the velocity? So probably the easiest is to assume the acceleration to be constant, no? Mm-hmm. Okay, so from that point of view, we could say that.
Can't you just use conservation of linear momentum? So it'd be, if it's stopped, it says it's stopping at rest, right?
Yeah, okay.
So I mean, you could say mass times velocity n would be whatever the impact force is, and then divided over the time, because it gives you the collision time, right? At 0.5 seconds.
Yeah.
So that's how you get force, right?
That would be a way to do it. And that would be a solution, but then it would have nothing to do with vibrations, no? But
well, it would be like a forced damped problem, right?
Yeah, I mean, we might do it that way. I like the way. Yes?
The spring force is going to change with the X position, and the damper force is going to change with the velocity, so I don't think it's reasonable to assume that the acceleration is constant.
Yeah, I know.
Or proportional to velocity, honestly.
I agree with you. The acceleration should be proportional to the velocity.
I don't think that particularly works either. Because then it would...
Because of the spring force.
Yeah.
Yeah, what happened is that the spring force, if it's linear, we can assume maybe the acceleration to be linear. So it will be, it will not be constant, but it should be a linear relation with the spring force. That's why I will solve this problem if it was a real life. I will say the acceleration is in function of the deformation of the spring. Does that make sense or not?
All right. Just curious, why wouldn't we use the normal method of making an equation of motion and all that and not worrying about what the acceleration is proportional to?
I mean, let's do that. But so we do the acceleration then for the system. But then what is your mass over here? You're taking the mass of the car when it's connected to this, no?
Mm-hmm. Suppose you can assume that to be massless.
No, you assume mass. So you assume the mass. You will assume this is the mass of the car. But what happens is that it counts with the momentum.
Mm-hmm.
So yeah, but it would be the mass of the car, no?
When they're connected, yes. At least that's how I read the problem.
I assumed critical damping because otherwise the car is going to bounce back at some point.
Yeah, you see, that's interesting. You see, when you make up problems, yeah, but then, okay. When I look at this problem, okay, when this is going to hit the bumper, is really equivalent to say that this would be equal to the mass of the car. No, the force being applied there is going to be a lot more than the weight of the car, because it's going to be from what is coming from the linear momentum. So what we need to find first is that what will be the equivalent force that will be impacting over here.
So you're saying to read it as a forced oscillation?
And then and then maybe there I will say, yeah, go to a forced oscillation and say for a constant value, no, for a constant force, see what would be the time it will take to damp it, let's say from 20 centimeters in 0.5 seconds.
Okay. The way I did the problem was I started from the moment of impact, and then said that the bumper panel there, I just kind of assumed it was massless, and then treated it as though the car were attached to the system and it was just had an initial velocity.
Okay. I mean, I'm not going to take anything as wrong or right, okay?
All right.
As long as you solve the problem consistently with your assumptions, I'm not going to say something is wrong or is right. But I think this one, the first step, what I would say is that, let's say first thing I would do maybe is to find the impact force at bumper. Okay? And I know because this is really going to deflect, no? But let's say this is extremely stiff. So what should be the maximum force you can have over there? You can say that V initial is what? 20 meters per second. And let's say, okay, would be 0, no? Yeah, I will put like 1 or 0.1, but let's be epsilon. So we know M equals 2,000 kilograms. So what I will say over here is applying principle of linear momentum and impulse. Okay, so I'm not going to redo the derivation, but basically it will be, if you want, we can do it. It should not be that complicated. What is this equation? Summation of forces equals to MA equals to M dV dt. That gives summation of forces dt equals to M dV. Okay? So this will be equals to summation of forces dt equal to M dV 0 to T. Let's say this would be from V1 to V2. Okay? So we can assume that the maximum force of the impact, let's say, will be F times T. We assume the force of the impact to be constant. So the assumption I'm making here for the integration is force of impact equals constant, no? So I can remove the force from outside the integral. So only have dt, and this will be equal to what? M v2 minus M v1. Okay? So here we have the force of the impact. I don't know why I'm getting any value here. It doesn't matter, we can just take the magnitude, will be equal to, so force of the impact will be equal to M V1 divided by T. So that will be the first thing I will do over here. So I don't know if you have a calculator, if you want, we can start putting values, but otherwise we can just solve it, conceptually, and then I just have a new. See, you're lucky, but you see what I'm doing here with the page at the back? I mean, it wasn't the way in my time, because I'm not that old, but like when my parents were going to school, you had to do that. We had like thick ones. I used a little bit. Thick ones, thick paper that you will put, because when you will, write with the, it's not a pen.
I use that in my checkbook to make sure it doesn't bleed through.
Yeah, I mean, but you had underneath, you had like a thick paper, so it could absorb the ink. It would not go through. How do you call those ones when you need to put the inks? You don't use them here.
Fountain pen?
The what?
Fountain pen?
Fountain pen probably is what it is. When in France they're pretty typical, you write with fountain pens. So in school, so they teach you. So you have so much ink falling once in a while, if you press too much, then you need to put behind this type of thing. So that reminds me when I was in school. So 2. So let's see, numerical application. We have the magnitude F of the force of impact will be equal to what? 2000 kilograms times, what was that, 20 meters per second?
Yep.
Divided by 0.5 seconds, so we're going to get that the force of the impact is, so F impact. So it should be this 4, so 40,000, 400,000, 80,000?
Yes, 80,000.
80,000 newtons. That's a lot. I mean, basically, with your assumption over there, if you were taking the mass, you were taking what? 2,000 times, let's say, 10, no? For the G acceleration, you're taking 20,000. Because the object is moving, actually, the force of the impact we're assuming now is 4 times the one if you adjust the weight, no? Okay? So just because the car is coming with velocity, it increases that force about 4 in our assumption. All right? But again, this is not 100% true, because the force is going to start deflecting, no? So it's going to start absorbing the force. But let's say this would be the really worst case scenario. All right? So now, yes, we can probably study this as the mass of this object. So now that the mass is attached to this one, we can assume this is the mass, and we can assume this becomes like a forcing function, like a force vibration, no? For a constant value. Okay? So how could we do this stuff? Did we do the equation for this?
Well, it's the standard equation of motion, right? And then instead of equal to 0, it's equal to the impact force.
Yeah.
Impact force, yeah.
Just then The problem is we also don't have the mass of the bumper, nor do we have the dent.
Yeah, but what you can do there is that now you can
Compared
assume
to the mass of the car.
you can assume to be the mass of the car plus O. You can assume to be the mass of the car. That's
Right,
it.
right.
Yeah, so I think now you can assume, so now, so that was step 1. 2, let's say, model the problem